Okay, so in the last lecture we had studied about wave packet, group velocity and phase velocity. So wave packet is what? The wave packet is actually a particle in the quantum mechanics is represented by a wave packet, and the velocity with which the wave packet moves is called as the uh, group velocity, and the velocity with which the component waves inside the wave packet moves is called as the phase velocity. That is basically the velocity with which the wave packet moves is called as the group velocity, and the velocity with which the phase of the group of waves moves is called as the phase velocity. Now this is Vg is a group velocity, and u is the phase velocity. It's given as omega by k. Okay, u phase velocity is given by omega by k, and this is valid. This is valid for an infinite number of monochromatic waves of continuously varying frequencies. Okay, this is valid for an infinite number of, as I said, that any wave can be represented as a superposition of infinite number of waves. So this is valid for an infinite number of monochromatic waves of continuously varying frequencies. And as I said that the group velocity, all the physically measurable quantities are transferred with the wave packet, that is group velocity. Okay. And that is here the energy which is associated with the wave is transferred by Vg. Hence all physically measurable quantities are transferred with Vg, where u does not transfer any physical measurable quantity. Only the phase is propagated. Only the phase is propagated with u. Okay, so that is why you are saying that from this relation u is equal to c square by v, or c square by v, that v is always less than c. So that is why u will be always greater than c, right? But it does not contradict the special. It does not contradict the special theory of relativity, because it is, you cannot measure. You can, it does not carry any energy. Phase velocity does not carry any energy. Okay, so these are the things. Okay, so now let us come to the next topic, that is relation between phase velocity and de Broglie wavelength. Relation between phase velocity and de Broglie wavelength. Okay, so relation between phase velocity and de Broglie wavelength. Okay, now how is the phase velocity? How the phase velocity can be written? Phase velocity can be written as like this. See here, phase velocity can be written as like this, that is mc square, the energy E by P. Okay, mc square is the energy and P is the momentum. So U can be written like this: U is equal to E by P. Right? Now E is what here? E is square root of P square C square plus m naught square C to the power 4. Right? So from here you can write U is equal to square root of P square C square plus m naught square C to the power 4 by P. So if you take square root of P square here, so what will you do here? You can write it like this: P square C square plus m naught square C to the power 4 by P square. Okay. So U is equal to, what you can write, p square will be common. So p square will be common. So what you can write, and c square from both the here you can take c square as common. So you can take c out like this, and then you can write 1 plus m naught square c square by p square. Okay, so this will be what? This will be c into square root of 1 plus m naught square c square by p square, right? This p, how you can write? Lambda is equal to h by p by de Broglie. We have to do de Broglie wavelength, right? So p, how you can write p? You can write h by lambda, so h square by lambda square. Okay, h square by lambda square. Now, so this will be what? C into square root of 1 plus m naught square c square by h square into lambda square. So this is the relation between where this lambda is what? Lambda is the de Broglie. Lambda is the de Broglie wavelength. Lambda is the de Broglie wavelength. So this is the relation between phase velocity and the de Broglie wavelength. So you can be asked to derive this, or you can get some problems regarding this. Okay. calculation of de Broglie wavelength. Calculation of the de Broglie wavelength of a particle. Calculation of the de Broglie wavelength of a particle of mass m and kinetic energy ek. Okay, calculation of the de Broglie wavelength of a particle of mass m and kinetic energy ek. Okay, so the total energy E will be what? ek plus the response energy m naught c square. Okay, so E is what here? E is square root of p square c square plus m naught square c to the power 4 is equal to ek plus m naught c square. Okay, so squaring both sides. What do you get? P square c square plus m naught square c to the power 4 is equal to ek square plus 2ek into m naught c square plus m naught square c to the power 4. Okay, so this cuts. So from here, what do you get? From here you will get p square c square is equal to this. So from here, what you will get? If you take p common, so what will you get here? You will get here square root of ek square plus 2ek into m naught c square by c. Okay, and de Broglie wavelength lambda will be what? Lambda will be h by p. So this will be h by p. So this will be what? hc by square root of ek square plus 2ek into m naught into c square. Okay, so this is the thing. So you have to remember these two formulas. Actually, you can get problems from this. U is equal to this, and this de Broglie wavelength lambda is equal to this thing. You can get problem. Okay, so these are the things. Now say this de Broglie hypothesis, what is that? Lambda is equal to h by p. Okay, now this is valid. I mean, actually this is any particle can be represented by a wave, but this is, question can come to you in your exam that prove that de Broglie's hypothesis cannot be this is not valid for macroscopic bodies. Okay, this is not valid for macroscopic bodies. I mean, the question come like this: that prove that the de Broglie hypothesis cannot be proved for macroscopic bodies. Why can it? What does this mean? It means that for macroscopic bodies you cannot have that is uh, macroscopic bodies cannot be represented by a wave. Okay, how will you do that? So lambda is equal to h by p. So what is the value of h? 6.62 into 10 raised to minus 34 joule second. SI unit I am taking. Okay, and p is what? M, mass into velocity. Okay, so let us take a macroscopic body. Say let us take myself. Okay, my mass is around, it is 85 kg. Okay, I am taking the SI unit only. 85 kg into my velocity is how much? My velocity is say if I run, if I am in motion, how much velocity can I attain? Say if I am driving by a car, then I can still attain 100, but say 50 meter per second. Okay, 50 meter per second, and this is 80 kg. Okay, now if you yeah, these are all very small. I mean 6.62 divided by 85 divided by 50. I mean these are very small. Ultimately the thing will come out like this only. 10 raised to minus 34 order only it will come. Okay, 10 lambda will be of the order of 10 raised to minus 34 meter. So what does this mean? 10 raised to minus 34 meter is very small wavelength. So what does this prove? That very small wavelength means I was doing here I was doing in this region that very small wavelength, although it is much smaller than this also. Perhaps you cannot see with the naked eye, so small, 10 raised to minus 34 meter. It is less than that of nano also. Nano is 10 raised to minus 9 meter. 1 angstrom is 10 raised to minus 10 meter. 1 Fermi is 10 raised to minus 14 meter. This is 10 raised to minus 24 meter. So minus 34 meter. So definitely this will be a particle. So definitely this will be a particle and not a wave. Okay, whereas if you go by microscopic bodies here, microscopic bodies, this is 10 raised to minus 34 only. Okay, divided by mass of say electron. Mass of electron is how much? Mass of electron is 9.1 into 10 raised to minus 31 kg. This is 6.62 into 10 9.1 10 raised to minus 31 kg into velocity of electron is how much? Velocity of electron is very high, of the order of 3 into 10 raised to 8 meter per second. Now you see ultimately what order comes here. The order which will come here is 10 raised to minus 34 plus 31, that is 10 raised to minus 3, and plus a minus 8, 10 raised to minus 11 meter here. This comes out 10 raised to minus 11 meter. So 10 raised to minus 11 meter still, I mean you can consider that as a wave. Okay, 10 raised to minus 11 meter you can consider as a wave. Okay, so that is why it is told that macroscopic bodies cannot form does not obey, macroscopic bodies does not obey, cannot be represented by a wave. It does not obey this de Broglie hypothesis. Okay, so now comes your experimental verification of de Broglie hypothesis. Experimental mental proof